Hi everyone, in this video we're going to go through 16E, the normal approximation to the binomial distribution. So remember, with a binomial distribution we're looking at number of trials, so N, and P is your probability of success. So in these diagrams you can see they kind of look similar, but up the top just tells us that we've got a different value of N and P as we go across or down the page. So let me just show you. Oops. Don't have my thing plugged in. So you can see for the first row, the number of trials is 10 and the probability of success changes as we go from left to right. So for the first one, let me just get my highlighter up. All right, we've got a probability of success is 0.2, then 0.5, and then 0.8. So it's increasing as we go across the page. 0.5, you can see it's pretty much symmetrical, whereas 0.2 is positively skewed and 0.8 is negatively skewed. Now, as we go down the page, our value of N increases. So it goes from 20 to 50 and then last of all, 100. So as your value of N increases, and doesn't matter what your p-value is, they represent a normal distribution, okay, as you can see here. All right, so just in this little paragraph here, we can see that if N is small and P is close to 0 or 1, these distributions are skewed. So we saw that in the first row, okay, where I drew the skewed for 0.2 and 0.8. Otherwise, they look remarkably symmetric. In fact, if N is large enough and P is not too close to 0 or 1, the binomial distribution is approximately normal. Moreover, the mean and standard deviation of this normal distribution agree with those of the binomial distribution. So if N is sufficiently large, okay, so it needs to be quite large. So you can see here in the last column we had N is 100, last row, sorry. The binomial random variable X will be approximately normally distributed with a mean of N times P and a standard deviation of the square root of NP times 1 minus P. And just one rule of thumb, both NP and N times 1 minus P must be greater than 5. Okay, so for a satisfactory approximation. So it's not always going to be normally distributed, but you saying basically if N times P is greater than 5 and N times 1 minus P, which is N times Q, is greater than 5, then it's a satisfactory approximation. All right, for example 9, I'm going to go to our textbook for the lady to go through the example.
In question 9, we're dealing with a sample of 1,000 people and we're asking them whether they are in favour or not in favour of the construction of a new freeway. So once we see a set of information like that, we're already starting to think that it might be binomial, where N equals 1,000 and the probability of success is 0.3. So I'm going to define my variable X as being the number of people found who are in favour of the freeway, where X is binomial with a sample size of 1,000 and a probability of success of 0.3. If we want the approximate probability that between 270 and 330 people are in favour of the new freeway, what we need to do is turn this binomial distribution into a normal distribution. Now we know that the binomial distribution and the normal distribution are very similar in shape and size as long as N is sufficiently large. So if I'm going to turn this into a normal distribution, I need to find what my mean and standard deviation is. So for binomial, the mean is found by doing N times P, which ends up being 300. And my standard deviation is a square root of NPQ, where Q is 1 minus P. So that's 1,000 times 0.3 times 0.7. Work that one through and we get a standard deviation of the square root of 210. So knowing that the normal distribution is quite similar to the binomial distribution, we can say that if x is between 270 and 330 on the binomial distribution, like so, when we transform that into the normal distribution, what we're saying is that this probability in here will be the same. So this probability here is equal to the probability that z is greater than z1 and less than z2. Now you can call these values whatever you like. It's just an idea that we've got two unknowns down here, but we want these probabilities here to be the same. So to find the values of z1 and z2, we're going to use the z-score formula, where our z value is equal to x minus the mean over the standard deviation. And for the other side, the value of the unknown over here will be its corresponding x value, which is 330, minus the mean over the standard deviation. When you work that one through, you can see that z has to be between negative 2.070 and 2.070. When you jump on your calculator and have a look at normal CDF, set this as being your lowest bound and this as being your upper bound, you'll get a value of 0.9616, which is the answer to 4 decimal places.
All right, so with that example also, when I was watching it, you don't have to convert the z-scores. You can just go straight ahead into your calculator and use 270 to 330. And you can see I've done that there. Square root of 210 is your standard deviation and your mean is 300, and you can see we get the same answer. Okay, so converting it into the z-scores isn't necessary unless it asks for it, but it doesn't in this case. So we can just deal with 270 to 330. All right, let me just close that down. Let's do some questions. So a sample of 100 people is drawn from a city in which it is known that 10% of the population is over 65 years of age. Okay, so let's just highlight. So 100 people, 10% are over 65 years of age. Find the approximate probability that the sample contains at least 15 people who are over 65 years of age, no more than 8 people who are over 65 years of age. All right, because we've got such a high number, so 100 is quite high for your value of n. So n equals 100. The probability of success is 10%. So if we convert that into a decimal, it's just 0.1. And your probability of failure, remember that is 1 minus p. So it's just going to be 0.9. Now, I didn't mention this earlier, but binomial distribution we use when you have a probability of success and failure. Okay, you only have two, so success or failure. All right, so let's work out the mean. So for binomial distribution, it's n times p. So in this one, we're going to have 100 times 0.1, which is 10. And let's work out the standard deviation. So that's just the square root of n times p times q. Now, if I just go up here quickly, remember 1 minus p is also q. So this is equal to the square root of n p q. Just writing q because it takes up less space. And all right, so we're going to have 100 times 0.1 times 0.9. All right, so we'll do that on the calculator. All right, so we get 9. All right, so for question A, at least 15 people who are over 16 years of age. So we're going from our lower limit is 15 and our upper limit is infinity. Oh no, sorry, 100. Oops. Okay, where's my calculator? All right, so we can just go to normal CDF. Now you could easily do this on binomial as well, but because we're looking at the normal distribution, we're going to do it using the normal distribution, so normal CDF. All right, you can't really see my calculator, so let me just scroll down. All right, so our lower limit is 15, our upper limit is 100, our standard deviation is 9, and our mean is 10. So we get 2893. All right, so we want the probability that x is greater than 15 or equal to. All right, so if you did that within the binomial, you'll get a very similar answer, but might not be exactly the same because we're doing an approximation, okay? All right, I've got a confession. This should have been the square root of 9, which is 3. So let's go back and change that answer. That's why I always need to check my answer. All right, let's go back to the calculator. All right, so I'm going to just highlight this. So my standard deviation should have been the square root of 9, so which is 3. So let me just change that to 3. And there we go. So that's the correct answer. So 0478. All right, for question B, we want no more than 8 people. So our lower limit is going to be 0 and our upper limit, so no more than 8. So we want the probability that x is less than or equal to 8. All right, let me just get my calculator up. And that's not the calculator. All right, so we can just highlight that. Oops. Highlight it and go down. So our first number is our lower limit, so 0. And then we're going to 8. All right, and our standard deviation and mean are the same. Oh, what did I do wrong? Oh, no. Didn't change that 15. 0. There we go. So 2521. All right, so that's the normal approximation. Okay, if we were to do the binomial distribution, you would probably get a similar answer. Okay, but probably not exactly the same. So, yeah, we'll move on. Question 4. A manufacturing process produces an average 40 defective items per 1,000. What is the approximate probability that a random sample size of 400 contains? So n is 400. Now our probability of success, we want defective. So that's going to be 40 out of 1,000. Okay, so we're just, we have to calculate the probability of success. So you can do that on your calculator. So 40 divided by 1,000, so 0.04. All right, and then probability of failure is 1 minus that, so it's going to be 0.96. All right, so for question, oh, actually, before we do that, let's do the mean and standard deviation. So the mean, so n times p, so n times, so 400 times 0.04. So 16. And the standard deviation, now I'll try not to forget to do the square root this time. So we've already done n times p, so I'm just going to do that. 16 times 0.96. All right, so the square root of 16 times 0.96. So 3. Now I probably should leave that as an exact value, so I'm going to do that again. 8 root 6 on 5. Okay, just because it's better to not round. All right, so for question A, at least 10 and no more than 20. So we're going to use a normal distribution to approximate, but you could also use the binomial distribution to be more accurate. So at least 10, so we want to be greater than or equal to 10 and no more than 20. And I just wrote 10 again. Next. All right, so I think questions 3 and 4, we probably should have used the binomial distribution, but if you did the binomial and I do the normal, then you can see that they're pretty much similar. Okay, so 10 to 20, standard deviation, let's go over here. So what did we have? 8 square root of 6 divided by 5, and the mean was 16. All right, so 7834. All right, I'm running out of time, so I'm just going to do B, just write the notation. So we want the probability 25 or more, and there's all my year 8s are going to start coming in starting the meeting, 25 or more, so X is greater than or equal to 25. So your lower limit is 25 and your upper limit is 400. All right, so you can do that using the binomial, but as I said, I'm showing you how it can be quite similar to the normal distribution because you've got a high number. All right, let's finish with question 6. I've got 2 minutes. So an examination consists of 25 multiple choice questions. Each question has 4 possible answers. That's important. At least 10 correct answers are required. So at least 10. Suppose that a student guesses the answer to each question. So, so n isn't very high, so n is 25. Each question has 4 possible answers, so the probability of success is 1 in 4. At least 10 correct answers are required to pass, so a pass is greater than or equal to 10. All right, so what is the approximate probability that the student will pass the exam? Okay, so we want the probability that X is greater than or equal to 10. So if we're doing the normal approximation, your mean is n times p, and your standard deviation is the square root of n times p times q. So n times p, we're going to have 25 times a quarter, and your standard deviation, we're going to have 25 times a quarter times 3/4, because q is 1 minus p. All right, so you can go ahead and do that. Question B, what is the approximate probability that a student guesses from 12 to 14 answers correctly? So you're now going between 12 and 14. All right, I'm going to leave it there just because I've got my year 8 class now, but I'm sure you'd be able to do that on your own. Okay, bye girls.